All right, today we're going to be talking about exponential equations, section 6.3. Or exponential functions. We'll be solving a few equations as well. So an exponential function, f of x, c, a to the x. The c that's in front is just a number. That's your initial value. The a is your growth or decay factor is what that's called. Okay, growth or decay. So initial value or initial amount. We'll call it. You don't call it value there, but initial value or initial amount. So things that grow exponentially would be bacteria. You know, the things that you've seen in biology class, something like that. Human cells and reproduction grow exponentially. Initial value is how many you start with. So if you had a certain amount of bacteria that you started with in a petri dish, that's your seed, or a certain amount of crystallized whatever salt or something like that. The crystals grow exponentially well as well. So, but the initial amount is what you start with. The growth factor, growth or decay factor. Growth factor, it's going to be a bigger number. Decay factor, it's a small fraction. It's a big number, it's going to grow. It's a small number, it's going to decay. That's how that's going to be indicated. X is your variable. That's just going to, be the exponent on that. So one of the things that we need to be able to do is recognize exponential growth. And so we're going to play this game is the set of ordered pairs exponential. If so, write the equation. Example A, let's just get a table here. 0, 1, 2, 3, and 4. And the y values to go with it are 5, 10, 20, 40, 80. One of the telltale signs of exponential growth or decay is that the numbers grow really fast. It's exponential growth, or they decrease really fast if it's exponential decay. Okay, so here we go within the span of 5 x values, we get from 5 all the way to 80. That's pretty fast. One of the other indicators is that it's not going by the same amount each time. Linear things go by the same amount. That's slope. If it's slope 4, it would increase by 4 each time. That sort of idea, or it's a steady increase. Here, between 5 and 10, it's 5 units. Between 10 and 20, it's 10 units. And between 20 and 40, it's 20 units. So we see there's a pattern, but it's not a steady, always the same amount pattern. So that's one of the clues to tell us that it's not linear. It could be something else. Exponential is what we're looking for, so that's what we're going to test for. But quadratic could be a possibility for some things. But we're going to check for exponential. And the way you check for exponential is you divide your y values. 10 divided by 5 is 2. 20 divided by 10, 2. 40 divided by 20, 2. 80 divided by 40, 2. It's the same every time. The ratio of the y values is the same every time. What that means is that is your growth factor. The growth factor would be 2. If the ratio of your y values, when you take them in order like that, is the same every single time, what that ratio is your growth factor every time. Okay, so the function, you'd have 2 to the x power. What's the initial amount? 5. What we started with was 5. So because Think about if you plugged in a 0 for x, 2 to the 0 power is how much? 1. 1. 1 times 5. 5. So that's why 5 is whatever the x value of a 0, that y value is your initial amount. So there would be an exponential function for the data that we're given there.
There would be a number in the place of
x. Only if we have to build. You're always going to have x in the function that you're. Your initial value could be 1, and then you wouldn't have a number in front there because it's 1. You just wouldn't have it there. Like there is a number in front. There's a 5 in front. There could be, but it's not very often. Not with what we're doing. X is 0 is always going to be your C. You can find it, and we'll look at how to find that. And for one we maybe don't have or something like that, we can find it. When we solve equations, I'll show you how to find it. Really, it's not hard. It's easy. So let's say we had this set. -1, 0, 1, 2, 3. So we got a negative x value. So 32, 16, 8, 4, and 2. And for some reason, you find up there. So what's the ratio of our y values? Because obviously we're going from 32 down to 2. So this would be growth or decay. Decay. If it's exponential, it's decay. So we're going to test, is it exponential? Divide them. 32 divided by 16 is, well, I did that backwards. 16 divided by 32. In order, the second one over the, like up here, we did 10 divided by 5. Second one over the first, it's always the backwards way. So that's 1/2. And then 8 over 16, that's still 1/2. We'll go ahead and it's 1/2 the whole way, right? So 1/2 is our what? Decay factor, growth factor. They're the same thing. There's no difference. What's our initial value? 16. 1/2. And I always put the fractions in parentheses there. I'm sorry. I wrote it's supposed to be 1 or 1/2. So not 1/4. I think I said 2 over 4 is, and I was already writing it, and I said 4 and wrote 4. All right, not too bad. Now, Hannah asked a great question. What if you don't have that value? What if you didn't have that ordered pair? How would you know what the initial amount was? We, say we don't know what C is. If we don't have that ordered pair, we can find it by using some of the others. Okay, so I'm going to use the easiest one that I can. It doesn't really matter which one I use because I've got an X and a Y value with these other ordered pairs. If I use 1 and 8 and plug them into that problem, that would be 8 is equal to C times 1/2 to the first power. What's 1/2 to the first power? 1/2. So we have 1/2 C is equal to 8. How do I get C by itself? Multiply by the reciprocal. And there, C is 16. Now, we had that ordered pair when we originally did this problem, but finding it is not very difficult. You just plug in one of your ordered pairs in for X, and it's going to, you've got numbers there, and it's just going to work out to where you can solve it for very, very easily. The 2 came from, what do you do? How do you get rid of 1/2? Multiply by 2. You can still find, you can solve it for C and get there. So there's 16, 1/2 the X. That's, if you got 0, comma, whatever, then you don't have to do that. But if you don't have it, then yes, you would have to solve for that. All right. So recognizing growth or decay, pretty easy thing. If the ratios aren't the same each time, it's not exponential. That's easy to recognize. All right, so describe transformation of y equals 2 to the x. If f of x equals 2 to the x plus 4. What does that do? Does it move left? Why is it up 4? It's not in parentheses. It's not with the x. It's on the outside there, so it's a plus 4. So that would be a vertical shift. Up 4. Been a little bit, but can't forget things that we're supposed to know already. Same instructions. Describe the transformation on 2 to the x if we had f of x is equal to 2 to the x minus 3. What does that do? To the right 3, because it's with the x. They may not have it written in parentheses, but we can visualize that the parentheses would be there, that's with the x, because it's written in the exponential part. So that would be right 3. F of x is equal to 2 to the negative x minus 5. Something with a couple of things happening. Reflection across the y-axis and not x. Yeah, it causes the x coordinates to change signs, not the y coordinates to change signs. So that's right. Y-axis is what we're reflecting across. And then what's the minus 5 do? So y'all remember those. We just hadn't done them in a little bit. So they're still. The shrinking is the number that's in front. And if it's a big number in front, the coefficient of x is horizontal. And the big number in front would be a horizontal shrink. Little number in front, like small fraction, like one third, 1/2, horizontal stretch. It's the opposite with on the outside. If it's not with the x, it's on the whole problem. A big number stretches it vertically. Small number shrinks it vertically. That's the way that works. Let's get to the real meat of the lesson today. Solving exponential equations. You guys have done this before. This is Algebra 2. Oh, again. Really, that's all this is. All right, so let's start with the easy thing. Let's say we had 2 to the x plus 5 equals 2 to the 8. The bases are the same. So what does that mean about the exponents? They have to be what? They have to be equal. Okay? If the bases are the same, we're dealing with an equation. If this is 2 to some power, and this is 2 to some power, and they're equal to each other, then that better be the same power on each side. So those exponents have to be equal to each other. So if we can get the bases the same, then we can get the answer to that. Yes, the bases, because they're the same. They essentially cancel each other out. And as we get into logarithms next week, we'll see what math actually takes them away. But with exponentials, with this section, we can think about exponential numbers and things like that and work. So here we have 2 to the x plus 1 and then a 16 on the other side. The bases aren't the same, right? So could we rewrite the 16 as a 2? What does it become? 2 to the 4th power. Then the bases are the same again. So we have x plus 1 is equal to 4. And solve that. Get x is equal to 3. Cake. All right. Those are easy. that's where we'll get into the logarithms. And that will be in this section. This section, you should be able to change them. I'd actually planned on combining this section in the next one. Since I work problems at the beginning, I don't have time today to teach it all. So we'll just keep it separate. It's my wife. Telling me how many people she's out of her classes. All right, so we have 3 to the 5x, and then 81. Could it be written as 3 to the power? 3 to the 4th. 81 is 3 to the 4th power. You can do that. If you're unsure of that and doing that in your head, some people have them memorized to a certain power. Just they've used them some. The folks that had Algebra 2 last semester are at an advantage on that because they've done this very recently. Some of you haven't done this recently. Don't forget, you got factor trees that you can build. 9 times 9 is 81. 3 and 3. So there's where the 3 to the 4th power comes from. 1, 2, 3, 4, 3. That's where that's coming from. Okay, so don't think you can't do that. You don't have to have all these numbers memorized. I don't expect that. That really wouldn't help you very much because you don't know what you're going for. You know, you're not looking for the cube root or anything here because you're not necessarily sure how many it would be. The factor tree is actually the better method there. So I'd say, so that's 5x is equal to 4. So what does x equal? 4/5. These are the more difficult ones when you got an x on both sides. And the bases aren't the same. So the bases aren't the same, you'll try to get the bases the same, right? 4 and 8, they're related, but how are they related exponentially? 2s, that's the key. The biggest mistake that happens here is that you try to relate them as, oh, that's 8's 4 times 2. I'm gonna make that 4, that 8 a 4. No, you need to make them both 2s. So the 4 becomes what? 2 squared. So that's how that's going to happen. And the 8 becomes 2 cubed. Because that's not exponential. 4 to what power would be 8? Or it would be a fractional power, and that's going to. So, I mean, you don't want to introduce fractional powers unless you have to. We don't have to at this point. So, why am I multiplying here? Yeah, well, the exponent rules are that if this is 2 squared to the 2x minus 1 technically, and the exponent rule is that you multiply when they're like that. That's the reason. So we have 2 to the 4x minus 2 equals 2 to the 3x. Same reason I'm multiplying 3 times x over there on the right hand side. So just got to remember multiply those, and then you set up your equation. 4x minus 2 equals 3x. And x would equal what? 2. Subtract 4 is -1. -2 divided by -1 is 2.
You said this is the bulk of the.
This is the meat of this particular of 6.3 is solving. Yeah. The first half of chapter 6 is pretty. The second half is if you remember the rules. If you just memorize the properties. If you don't memorize the properties, you can't do it. We'll talk about that on Tuesday. The log properties.
I was going to say, because I don't remember them now. Yeah. You said that.
They're easy. You just got to refresh them. All right, so here we have a fraction in there. These get a little difficult when they're fractions because we got to remember how does that become an exponential. What exponential relates 9 and 27?
3.
3. Okay, so 9 becomes 3 what? Squared. So that side is going to be 3 to the 4x, right? What about this left side, which is a fraction? Good. 3 to the negative third. Because 27 is 3 cubed, right? If it's on the bottom, it's a negative exponent. So that's 3 to the negative 3 is what that turns into. 9 is 3 squared.
Yeah.
2, the squared times 2x is 4. 2 times 4. The squared is 2. So 2 times 4. 2 is 4x. And then so that's negative 3 equals 4x. X is negative 4 or 3/4. It's not. It's getting harder. Because he put a squared on the exponent. We gotta remember how to solve quadratics. So we've already done a problem that had a 4 and an 8 as a base. Exponentially, 4 and 8 are related how? As 2's. So that's 2 to the 6x squared equals 2 to the 3x, right? Y'all with me there? I don't want to. What part of the last part?
The 1 over 27 going to 3 to the negative.
If 27 is 3 to the third power, if it's in the denominator, make that exponent negative. That's all you need to remember. If it's in the denominator, it's going to be a negative exponent. That's the best thing I can tell you. I don't really know there's any other tricks to that. All right, so now we got that. So we set 6x squared equal to 3x. How do we have to solve this? Get it equal to 0 first. Because it's got an exponent on it. So that's 6x squared minus 3x equals 0. Factor out a 3x. 2x minus 1. 3x equals 0. 2x minus 1 equals 0. X equals 0. 2x minus 1 is, or 2x equals 1. I meant to write there. So x would be 1/2. Very important that you check your answer to make sure it works. Both of these do work in this problem. If you plug them back into the original problem, 4 to the 3x squared, yeah. That'd be 4 to the 0 power, which is 1. The other side, 8 to the 0 power is 1. If I plug in a 1/2, 1/2 squared is 1/4. 4 to the 3/4, is that equal to 8 to the 1/2? It is. 4 to the 3/4 turns into 64. 4 through to 64. Which works out really nicely. So the same thing as the square root of 8.
So here's the exponent on the exponent.
You've got to get it equal to 0 and solve it using the methods that we've done with quadratics, polynomials, and that sort of thing.
And if the power, if it's a number with power to 0.
Anything to the 0 power is 1, yes. Anything to the 0 power is 1.
I'm comparing those last two. This side has each row that's 2 to the 3x. The other side, you got 3 to the 4x. 2 to the third power, I know is 8.
Mm-hmm.
The 3 to the 4th is 81 or something.
Right, but this was 9 squared over here. 9 to the 2x would be, the 2 part would be. I broke it down to get a base of a 3. 9 is 3 squared.
Yeah.
3 squared to the 2x, and it turns up to 3 to the 4x. You multiply those exponents. 2x times 2. So I got the 4x.
So you're trying to find what?
In between, this is what's happening. These two multiply together. 3 squared is what 9 is. These two exponents multiply together to get me that 4x. That's the in between that was happening there that we did kind of in your head there. That'll be the next section. We'll start talking about logarithms because there's not a way to exponentially relate those. The ones in this section are exponentially related. We don't have the. You may know how to solve those from Algebra 2, but it's not. We're not doing that yet. So we'll get to those next week, I promise. I know they're itching to solve hard problems. Example L, e to the 2x equals e to the x minus 5. That e is the e from Algebra 2, the exponential number. It's like 2.71 and some change. It's a number like pi. It's represented by a letter. You know, it's a symbol for a number. But the base, it really doesn't matter what the base is. If they're the same, then you can solve those, right? The base is the same, so we can set this problem as 2x equals x minus 5. Do I have to get this one equal to 0? Why not? There's no exponent on the variables, right? So that's when you know to get it equal to 0, so the exponent on the variables. So here we're just going to subtract x, get x equals negative 5. Out of that. Real easy stuff. E to the first power. If you did that with your calculator. E is over here to the left. Second ln. And 2.7182818. And it keeps going on forever. We'll talk about when you have to use logarithms to solve things like that, and we'll get to that next week.
So why didn't you do the same for 2x?
I did. 2x minus x is x. 2x minus 1x is 1x, and that left me the negative 5 there. That's what I did with it. Just didn't write it down. E to the 7x times e to the x squared equals e to the negative 12. Got to remember some exponent rules here, because the bases are the same on the left-hand side. So what does that mean you do with those exponents? You add them because they're multiplying. So that's e to the x squared plus 7x. And I wrote it in that order because it's descending order, right? Because we know, what are we doing next? Setting the exponents equal to each other, right? Very good. And we got to get it equal to 0 because it's got x squared in the problem. So we have x squared plus 7x plus 12 equals 0, which is a quadratic. We had a whole section in chapter 4 about solving quadratics. And we had a whole chapter about solving large polynomials. We should be able to do this. How do we solve that?
X plus 4.
Yeah, you could factor it at x plus 4 and x plus 3. You could do quadratic formula if you wanted to. X equals negative a plus minus radical b squared minus 4ac divided by 2a. You could do that if you want to. Either way, factoring is what we're doing because it's quicker. So x equals negative 4 and negative 3. Technically, you should check both of those. They both work. You plug them back in.
How did you get? Never mind. So
You got it?
Yeah, I figured it out. So you plug
Negative 4 into for x here, so you got e to the negative 28 times e to the 16. And does that equal e to the negative 12?
So you have to check both?
Yeah, you got to check each one individually. They both work in this problem. All right. Doesn't get much more complicated than those, honestly. So skipping a few problems that I don't want you to do in there is the reason for that fun little list of problems to practice. And that'll get us into 6.3. Again, you guys ask great questions about what if this happens. We're going to get to those what ifs next week when we throw the logarithms in there as well. So easy stuff in